Right, pressure. Obviously, this only affects equilibria that involve at least one gas. So, what's the general idea? If I increase the pressure, the equilibrium will shift in the direction of fewer moles or molecules in order to try and decrease the pressure again. So fewer moles and molecules will mean less pressure. If I decrease the pressure, this will cause the equilibrium to shift in the direction of more moles in order to make more moles, molecules, and to increase the pressure again, to resist the change. Okay, let's look at an example. The contact process for making sulfuric acid. The reversible reaction in this process looks like this. Now, the first thing you should do in these cases is count how many moles or how many molecules you have on one side of the equilibrium. Here we've got 1, 2, 3, and on the right hand side we've got 2. So there's 3 moles on the left hand side, or molecules, and 2 moles on the right hand side. So what happens if we increase the pressure here? Well, if we increase the pressure on this system, then it will shift in the direction of fewer moles, so it will shift to the right. So increasing the pressure would cause the production of more of the product, sulfur trioxide. If we look at the hydrogen and iodine reaction that we saw before, how many moles are on the left-hand side? 1, 2. How many moles on the right-hand side? 2. So, what would happen if we increase the pressure here? 2 moles on the left-hand side, 2 moles on the right-hand side. What will happen? Nothing. Because there's no way the equilibrium can shift in order to try and decrease the pressure again. So it's a bit of a trick question, that one, but it's worth knowing. Temperature. Now, we've talked about in the last section about the changes of energy when a chemical reaction takes place. So we have to be given, in this case, we have to be given some information about whether the forward reaction is exothermic or endothermic. So forward reaction exothermic here, that's the information given. That would mean that the reverse reaction is endothermic. Obviously, it's the opposite process. Think back to your energy level diagrams. So, what would happen if we increase the temperature to the position of equilibrium? We need to describe and explain these things. So, if I increase the temperature, then this reaction, this system will shift in order to try and decrease the temperature again. So if I increase the temperature, reactions at equilibrium shift in the endothermic direction to try and decrease the temperature. So here, the equilibrium would shift to the left. We would get more of the reactants and less of the product. Why? Well, as we've just said, it will shift in the endothermic direction in order to try and decrease the temperature, to resist the increasing temperature. Think about that for a second. I could also have said what would happen if I decrease the temperature here. If I decrease the temperature of this system, it will shift in the exothermic direction in order to try and increase the temperature again. So if I decrease the temperature, then the equilibrium would shift to the right in the exothermic direction in order to try and increase the temperature. This is something we'll talk about later on, but what would be the best temperature to use if we want to make more ammonia? Well, the best temperature, following this logic, would be a low temperature, because that would make more of the ammonia. Catalysts. Now we know that catalysts, they increase the rate of chemical reactions, but they do not affect the position of equilibrium. So in a reversible reaction, if I add a catalyst, it doesn't affect the position of equilibrium. But what it does is it increases the rate at which equilibrium is reached. A catalyst increases the rate of the forward and reverse reactions, so it increases the rate at which equilibrium is reached, but it doesn't affect the position of equilibrium. A couple of things for you to remember. In the Haber process, we use iron as a catalyst, and in the contact process, we use vanadium 5 oxide as a catalyst, both in the solid state. Right, I think that's about it. Have a look at the pages indicated and answer the questions.